So good afternoon again. It is my pleasure now to present to you Matteo Forconi. He's a postdoc student at the University of Ferrara in Italy. And today he will be talking to us about the consequences of misusing sigma 8 in cosmology. So please, Matteo, start whenever you feel ready.
Thank you, Enrico and Maddi, also to give me the opportunity to present this work here at the CosmoVerse JournalClub. So this work has been done in collaboration with Arianna Favale and Andrea Gomez-Valent, and is about illustrating the consequence of a misuse of sigma 8 in cosmology. So the outline of the talk will be as follows. So I will briefly introduce what sigma 8 is, even though maybe you are all familiar about this parameter, and what are the state of the art of the constraints. Then why, when we talk about growth tension, we are also talking about sigma 8, and which are the caveats that come from the definition of this parameter. Then, starting from these caveats, we're going to see why it might be an advantage for us to use a new parameter called sigma 12. And then after understanding if we are actually nitpicking on why, by choosing sigma 12 instead of sigma 8, we're going to compute some biases and do a simple model comparison. So sigma 8 actually is the root mean square of the amplitude of density perturbation at a particular scale. So we know delta is the matter density contrast, and it is averaged. And in this case, we talk about sigma r because we convolve the matter power spectrum with the window function. In this case, represented here in the slides, the top hat window function, which depends on a certain scale r. And for this reason, we say that it is moving on a certain sphere for a certain radius. And in this plot, we can see the behavior of this window function for different radius. And what is important is that this sigma kind of characterizes the large-scale structure fluctuations at linear level. Now, this sigma r is given in h-1 MPC units. And the reason why is mostly for historical reason, and it was at first used in galaxy redshift surveys, these units of measurements. And the reason why is because at low redshift, the distance, the comoving distance can be approximated by a redshift of c over h naught. And therefore, these units kind of are model independent from the underlying fiducial cosmology that we are using. The issue starts when we are using these units also in other instances of cosmology. So we are talking about sigma 8 because with this root mean square amplitude smoothed on a particular scale are computed at a scale of 8 in these units, so h-1 megaparsec, and therefore we call it sigma 8. Now, sigma 8, we can have constraints of sigma 8 from early universe, which means we can use the CMB and the fitting model parameters that we got from the CMB, and we can derive, evolve these parameters, the density parameters, and actually put some constraints on the derived parameter, which are sigma 8. On the other hand, we can also use late universe observations, for example, with gravitational lensing, redshift space distortion, galaxy cluster. These are low redshift, and they can put a constraint of sigma 8, which is better on S8, which is a combination of sigma 8 and omega matter, but they rely on a certain fiducial cosmology. So, as we are talking about early universe, late universe, I think we all think about the same stuff. So this is bringing us probably to a new tension, like H-naught tension. Now we are talking about growth tension. So there is this tension between the late time and early measurements. There's a little caveat to that. This tension might not be a tension anymore due to latest observations from kids and combination between kids and DESI. However, there is still around this. So this plot is taken from the CosmoVerse white paper, and as you can see, there are some tension from measurement of S8. Now, this is important because this growth tension, or also called sigma 8 tension, is intertwined with the Hubble tension. So as you can see, we have a similar plot here because again, we have these disagreements between early and late time measurements. And this is kind of important because solution to Hubble tension. So when we try to solve Hubble tension, we propose alternative models to lambda CDM, and the solution tends to increase sigma 8 so to exacerbate this growth tension, because the increase in sigma 8 means that we are going far away from late time measurements. Now, for this reason, also have been proposed a plethora of different models to solve this tension. Here is another example. All these plots are taken from the CosmoVerse white paper. So there are different models that want to try to tackle this sigma 8 problem. Now, let's put it this way. We have a different dots of different measurements, problem that we want to solve, maybe with a single model there. And we want to fit all these different dots in cosmology. Our ultimate goal would be to try to find the ultimate model, right? And by seeing these dots, we might say, okay, it might be a Horse solution. But if we are able to just erase some of these points, because maybe these are not proper points. In this case, maybe if we're able to see that the sigma tension is not a tension anymore, then we can get rid of one point and then understand that this O's, in fact, is a piano. In my head, it was clear what this metaphor want to picture. I'm not sure if that's clear, but anyway, the point is it worth it? I mean, if we're able to get rid of one of these points, which is the growth tension in this case, we might find different model, different solution for understanding our universe. So it's important also to underline that our work is sitting on shoulders of a previous work being done by Sanchez in 2020, which he is firstly like arguments against the using of these units of h-1 megaparsec in observational cosmology. The reason why is because they depends on h. So the scale depends on h, and this can introduce biases either in the interpretation of large-scale structure measurements, and also on the results that we have sigma 8 obtaining from different cosmological models. So we can think about two different ways. Either we have different measurements with different h0 priors that can, I mean, it's difficult to compare if we are using a scale that depends on h, or we can also have difficulty to compare the sigma 8 constraints from different models that have different posteriors on h0. So, for example, let's look at these plots here. As you can see, there is some tension between Planck, Des, and Bose. But if you look at the posteriors of H, we see that we have different posteriors. What happens? So how can we get rid of this tension? I mean, how can we clean these from this bias? Well, an obvious and simple, really simple solution is to fix the scale or get rid of this H dependency. So as I said, these late-time measurements rely on a fiducial lambda CDM model, and therefore we can, for example, fix our H to the CMB data H in the sense that is 0.67. And if we fix, which is usually the fiducial model under these observations, and if we fix to 0.67, what happened is that our scale becomes the 12 megaparsec. And if we fix that scale, we see that we can read off one of these tension between, for example, Des and Planck, as you can see here in these plots from the green and blue contours plots. Now, this is clearly show you at the beginning that sigma 12 might be a better parameter rather than sigma 8 to truly understand the tension between these measurements. Now, this is a reason why we want to get rid of sigma 8, but I also can tell you why we prefer to use sigma 12, because we are fixing the scale where we are computing this amplitude of matter perturbations. Now, are we nitpicking in the sense that this is just a virtuosism, or it's something that we really need to compute and it's important to get rid of this parameter? Well, let's just do a simple experiment, let's say. So if we fix all the cosmology and we take different value of H0, what we are doing is that we are fixing the evolution up to low redshift, where since we are taking different values of H0, we are changing the cosmological constant. That means that this is relevant at redshift which are less than 1, so we are expecting effects at this low redshift. As well as we are expecting that if we have larger values of cosmological constant, then we have smaller matter fluctuation. Definitely, that's not what we are seeing here. So these three curves, which represent sigma 8, we got these curves by fixing the parameter and changing H. As you can see, we see effects also a higher redshift, as well as we are seeing a decrease of the curve when we are decreasing H. So exactly the opposite. Whereas if you move to the sigma 12 parameters, we see that everything is as we expect. So, of course, we are not nitpicking because this is theoretically wrong to compare these curves of sigma 8, because we are just comparing amplitude of fluctuations at different scale. This is not the case for sigma 12. Then also, if you look at these plots here, we compute the differences between sigma 12 and sigma 8 and sigma 12 to understand if you are able to actually see, to measure this difference. And yes, that is the case. As you can see, red dots, this is redshift space distortion measurements. In the red dots, we are able to see when the H parameter is near the shoes values. But we compute also the AC forecast, we connect the dots, and we see that we are able, actually we are sensitive to these differences. And if you also think that CMB data constraint sigma 8 already at 1-2% level, then we can see this difference if we change the parameter. Now, we can compute semi-analytically these differences if we just Taylor expand for sigma 12. You can compute the bias. As you can see here, sigma 8 and sigma 12 are the differences is redshift independent, because sigma 12 is not changing in this case, but that depends on delta H. So that is what we are actually seeing on the plots there. So the difference depends on H. So we are expecting already that if our H value is around the fiducial model used to obtain sigma 8, then sigma 8 and sigma 12 are almost similar. Now we understand that it's not nitpicking, because otherwise also not only theoretically wrong, but also observationally relevant. And let's look at what is the bias if you use redshift space distortion and peculiar velocities measurements. What happened when we change sigma 8 to sigma 12? So first of all, we have, so the measured power spectrum has these, depends on this ratio, which is, since sigma r represents the amplitude of the power spectrum, we expect this ratio to be dependent also on the parameters that affect the shape. But this is not the case if R is sigma 8, because sigma 8 depends also on H, which influences also the amplitude of the matter power spectrum. And then what Galaxy Surveys constraints is F sigma R, which again usually is F sigma 8. But since they depend on a fiducial lambda CDM cosmology, and I've told you that we use the CMB Planck fiducial cosmology, we can approximate F sigma 8 to F sigma 12. So we don't have to change these measurements. We can use them, but we can think of them like to be on F sigma 12. Now, of course, this is a first approximation. Now, if we try to compute this bias, what we need to do? So we need to define this growth rate parameter, so the growth rate parameter in this way. Then we have the evolution parameter, which allows us to measure like this the evolution of this density contrast. And we assume a lambda CDM. And with all of that, we are able to constrain, using redshift space distortion and peculiar velocities measurements, gamma and sigma R today. So gamma governs the evolution of perturbation with cosmic expansion, while sigma naught determines the present-day amplitude of the power spectrum at the scale R. Now, since we can say that redshift space distortion can be either measured F sigma 8 or F sigma 12, since they are similar with that fiducial cosmology, what we've done is this. So we have tried to test if they are actually measuring F sigma 12, and it is the black curve there, or if they're measuring F sigma 8, and then we deriving the constraints on F sigma 12 using that Taylor expansion. What happens is that if we impose a shoes prior, therefore we kind of simulating the idea if we are using a model which predicts higher value of H naught, we are kind of introducing a bias of 1 sigma to this model. We are penalizing them because we are considering redshift space distortion and peculiar velocity measurements are measuring F sigma 8. So of course, the red and then black holes are overlapping because in that case, the prior is from Planck. So again, is around 0.67. So where we actually expanded the correction of F sigma 12. Now, here we see there is a 1 sigma bias of sigma biases on the models if we put an H0 prior from shoes. And eventually, we can compute this by doing a model comparison. And to do that, we choose some models that are being used to try to solve the H0 tension. And as datasets, we combine Planck, Daisy, and eBOS Pantheon with shoes because we want to exacerbate the value of H0 that we found. And as you can see here, the results, it is known that anisotropic 3D BO data do not give room for just late time solution to solve the Hubble tension. So for example, for CPL parameterization, which is WWA CDM, we don't have an increase of H0, whereas as expected, we have for the other three models, so that employ the neutrino physics or early dark energy, we have an increasing of H0. So we are actually going towards easing the H0 tension. But now let's look at the sigma's value. As you can see, sigma 8 is behaving like it's increasing when we are increasing H0, and it's behaving differently with respect to sigma 12. Now, just to show you for completeness, we compute a simple AAC for this model, which is a simple statistical tool. And as expected, early dark energy is the one with highest value of AAC, so it's preferred by the data. But the point is that by looking at sigma 8, we see we are exacerbating this growth tension, so we cannot think of this model as the solution. However, by looking at sigma 12, we see that these measurements are stable. And the reason why this large increase on sigma 8 is due to the fact that the value of R8, so this scale at 8 H-1 megaparsec, are substantially smaller than R12, which is this vertical dashed line, even if, for example, in lambda CDM or CPL in CPL model, because we are using a combination of different data which are rather increasing H with respect to the simple H where we did the Taylor expansion. So as a result, the comparison of the sigma 8 curves obtained from this MCMC for the various model are, let me say, meaningless in the sense that they represent amplitude of fluctuation at entirely different scales, as you can see here. So let's just put all these results in these plots. I mean, the most important results is this plot here. So you can see that the value of sigma 8 are fluctuating a lot. So you have in each horizontal plot and each stripe, you have the value of sigma 8 and sigma 12 at different redshift. And as you can see, sigma 8 is fluctuating a lot, whereas sigma 12 is stable, is within 1 sigma for all different models. So that means that, for example, in this case, let's talk about the early dark energy, which is the model more penalized by the sigma 8. And we can see that in this case, sigma 12 remains stable at 1 sigma for early dark energy. And therefore, we are, by using sigma 8, we conclude that early dark energy produces significantly greater clustering in the universe than the standard model. And therefore, early dark energy is able only to solve Hubble tension at the expense of worsening the growth tension. But this is not the case if we are looking at sigma 12. And for example, just as a small exercise, which is, of course, has to be done with more precision, but just to give you an idea, if we compute the chi-square with the best fit of this model taken with Planck, Daisy, and Pantheon Plus, and shoes, and if we use redshift space distortion and peculiar velocity data has to be on F sigma 8, we obtain a chi-square of 118. Whereas if you took them as measurement of F sigma 12, the chi-square is really small, and now it's not penalizing this model anymore. This is the case for early dark energy, but it's the same for all the other models. So with this, I conclude this talk and this presentation. I hope I was able to present you the sigma 12 parameter as the right parameter to actually compare large scale structure measurements. And the idea is that sigma 8 is tied to the H0 distribution. And therefore, it cannot be used for, as I said, fair model comparison, specifically for models that want to change this H0 parameter from the CMB value towards the shoes values. Because it introduces a bias, and sigma 12 actually define the amplitude at a fixed scale, and therefore it's more stable for the different models, and it can represent better what is happening at the linear variant matter perturbations. So thank you for your attention, please.